We're going to continue working practice exercises using the problem-solving strategy for substitution and elimination reactions. In this example, we have a cyclic alkyl halide. First, we need to identify the leaving group. In this case, it is the chloride ion which will leave. Also notice that this is a tertiary alkyl halide. So we'll mark that off on our sheet. We know that tertiary alkyl halides can undergo only three kinds of reactions: SN1, E1, and E2 reactions. That will be dependent upon what kind of nucleophile or base is participating in this reaction. Finally, notice that on our substrate, we have two chiral centers. One chiral center is located where our leaving group is, so we'll have to consider that in our product structures. The other leaving group is on another carbon which is not participating in our reaction, and it will not change throughout the course of the reaction. Now we'll look at our nucleophile or base. In this case, we have acetic acid. Acetic acid is a carboxylic acid and not a base, so we can remove any kind of base from consideration. That leaves us with nucleophile. Because there are no negative charges here, this is a weak nucleophile. And with a weak nucleophile, that eliminates E2 reactions from our list, so we're left with SN1 and E1 reactions. In either case, the first step of either reaction is the same, and that is the leaving group leaves and takes its electrons with it. This carbon originally had 4 bonds, it now has 3, and because the chlorine took its electrons with it, it is electron deficient, leaving behind a carbocation, and of course the methyl group is still there. Because this is a weak nucleophile, there are 2 competing reactions that take place, and that is the SN1 and E1. We're going to work this example through as SN1 first, and then go through as E1, and then discuss the differences between the 2 reactions and how to control which reaction happens. So first, SN1. In SN1, the electrons here on this oxygen come and attack this carbocation, forming a new bond. Notice, though, that this oxygen before had 2 bonds and has now made a third. This oxygen will become positively charged. The chloride ion, which left before, will come back and remove this hydrogen, allowing the product structures to be formed. Let's look at the products of the SN1 reaction. Because the intermediate is a carbocation, it has sp2 hybridization and trigonal planar geometry. This means it's flat, allowing the oxygen of the acetic acid to attack from either the front face or the back face. In one case, with the oxygen attacking from the front, the methyl gets pushed to the back, and we have this product. In the other structure, the oxygen attacks from the back and the methyl gets pushed forward. Because the intermediate is sp2 hybridized and flat, the oxygen can attack from either the front or the back in equal amounts. These 2 structures are diastereomers because one chiral center remains the same while the other changes. If we do the checking of the priority groups, we find that this one is R and this one is S, and they form in equal amounts. This is a diastereomer mixture. Next, we'll look at the elimination products. The elimination reaction begins exactly the same as the substitution reaction. The chlorine leaves, and that leaves behind the tertiary carbocation. However, unlike the substitution reaction, the oxygen of the acetic acid is not going to attack the carbocation and form a new bond. However, it is going to take a proton from either this adjacent carbon, or this adjacent carbon. So the oxygen uses its electrons and forms a new bond with the hydrogen. The electrons that were in this bond with the hydrogen move over and form a new pi bond between these 2 carbons. This eliminates the carbocation because this now has a full complete octet and 4 bonds. Let's examine the product structures. Now let's examine our reaction products. It's important to keep in mind that elimination reactions of secondary and tertiary alkyl halides can form multiple products. So it's important to draw the structure of each possible product and examine it carefully, as some of them may be the same. At the same time, it's also important to reevaluate any chiral centers in the molecule because they may have changed due to the configuration change in the product. In our first product here, a hydrogen was eliminated from this carbon here, forming a new pi bond here. Notice that reevaluating our stereochemistry, we still have S configuration here. In our second product, We abstracted a hydrogen from this CH2, leading to a double bond here. And again, reevaluating our stereochemistry, we still have S. In our third product, the hydrogen was eliminated from the methyl group on the outside of the ring, so the double bond is now on the outside of the ring as well. The stereochemistry here is still S. As I said before, substitution and elimination reactions are competing processes. In our example, we worked through the problem using both reaction mechanisms. Both of them are possible. However, through temperature control, we can drive the reaction towards one mechanism or the other. Substitution reactions are normally favored at room temperature or below, and elimination reactions are favored at room temperature or above. When working problems or on an exam, it's important to examine your reaction conditions carefully, as this will give you a clue to which reaction mechanism will take place. Again, it is also important to draw all of your structures and examine them carefully and to reconsider stereochemistry at all steps. In our example, it just so happens that we turned out we had the same stereochemistry at the end. However, this may not be the case for all problems.